Now this was a slide to kind of review what the stratified Cox model is and how it compares with the proportional hazards model that in which you're not stratifying on anything. So there were 5 models here. Just to review this, there were 5 models listed here, and we went over which kind of model is which here. And the first one I asked you, model 1, what kind of a model is that? Is that a Cox proportional hazards model or is it a stratified Cox model? And the answer was it's a Cox proportional hazards model, not a stratified Cox model, because you don't see a subscript G that indicates the G stratum. And it's a proportional hazards model because every variable, there are 3 variables in this model, they're all in the model. Now, let me ask you this. For this model, if the treatment variable here was a binary variable, a 0-1 variable, for this model, what's the formula for the hazard ratio for the effective treatment? What is it? E to the beta 1. There's no interaction term in this model, right? So it's just e to the beta 1. That's the usual formula. Okay? Okay, next model, model 2, and model 3. Model 2. What kind of a model is this? Well, we know it's a stratified Cox model because we see the subscript G. What kind of a stratified Cox model is it? Is it a no interaction stratified Cox model or an interaction stratified Cox model? I'm trying to review this. It's a no interaction stratified Cox model. Why? Because the subscripts of the variable of the parameters corresponding to the variables in the model don't have a G there to distinguish different strata. So this is an example of a no interaction stratified Cox model. Now for this model, what's the formula for the hazard ratio for the effect of the treatment variable using model 2? It's also e to the beta 1, right? The coefficient of the treatment variable. Will that be the same value as you would have gotten if you did model 1? No, because in model 1, you're assuming that the variable sex satisfies the assumption. In model 2, you're stratifying on it, right? So you're not necessarily going to get the same value for the hazard ratio because you're fitting 2 different models. In one case, you're stratifying on a variable you may decide doesn't satisfy the assumption. And with the data that we had, model 2 we saw was better than model 1. Okay, so I'm reviewing what we did. Okay, what about model 3? What kind of a model is that? Well, we know it's a stratified Cox model. Is it a no interaction model or an interaction stratified Cox model? Now, by this time, you know the answer, right? It's an interaction stratified Cox model. How do you know it's an interaction stratified Cox model? Because the coefficients of the subscripts of the parameters in the model have G subscripts, right? That means so what's the effect of the treatment variable in model 3? It's a hazard ratio. What's the formula for the hazard ratio? It's e to the beta 1G, where G depends upon whether you're male or female. So you're going to get a different value for the hazard ratio whether you're male or female, and that's what you mean by interaction. And there's an interaction of the variable you're stratifying on with the variables that are in the model. Okay? Got that? Okay. What about model 4? What kind of a model is that? Well, we know it's a stratified Cox model because you see the subscript G. What kind of a model is it? What kind of a stratified Cox model? Is it a no interaction stratified Cox or an interaction stratified Cox model? It's an interaction stratified Cox model because I showed you last time that you could write an interaction stratified Cox model 2 ways. One way, you could sort of write it where you separate the data into the strata. In other words, if you have 2 strata, males and females, you separate the data into a model for males and then you get a model for females. So you separate it into 2 models. Alternatively, you can use one model to incorporate the interaction by putting in the 2 variables that you say are okay, and then putting in product terms among the variables that are okay with the variable you're stratifying on. And then still stratifying on sex. That's what the G is saying, I'm still stratifying on sex. So for this model, what's the formula for the hazard ratio for the effective treatment? What's the formula for it? In model 4, it's e to the what? Beta 1 plus what? E to the beta 1 plus beta 3 times sex, because there's a product term here of treatment with sex. So it's e to the 1 plus beta 3 times sex. And what does that mean? That means you're going to get a different hazard ratio depending upon whether you're male or female. When you plug in the value of sex equal 1 or sex equals 0, you're going to get a different hazard ratio. So this model 4 is basically equivalent to model 3. They're just two ways of doing the same thing. Okay, and you can. One of the advantages of using model 4 is that if you look at model 4 and you ask and you want to compare the no interaction model to the interaction model, what would you do? I talked about that. How would you compare the no interaction model to the interaction model? Well, what you do is you do a likelihood ratio test, right? And to do a likelihood ratio test, you're comparing two models. What are the two models? Model 4 with model 2, right? And so you would run model 4, you'd run model 2, you'd get minus 2 log the maximized likelihood for each model, subtract one from the other, and the degrees of freedom would be? What would it be? How do you know it's 2? Because to go from this model 4 to model 2, if beta 3 and beta 4 are both equal to 0, then the reduced model is model 2. So you set beta 3 and beta 4 equal to 0, which are two parameters. That's why the degrees of freedom is 2. Okay, that's how it works. Questions about that? Okay, what about model 5? Cox model? Yes. Stratified Cox? No, because you don't see a subscript G in there. And is it an interaction model or a no interaction model? It's an interaction model, but it's assuming that the proportional hazard assumption is satisfied for every variable in the model. So what's the formula for the hazard ratio for the effective treatment in model 5? What is it? It's e to the beta 1 plus beta 4 times sex, right? Well, it's now, previously it was beta 3 times sex, so you're not necessarily, even the formula is different, but when you run model 5 and you run model 4, you're going to get two hazard ratios, but they're not necessarily going to be the same, because one of them assumes that the sex variable satisfies the assumption, as does all the other variables, and the model 4 doesn't. Okay, so that's stratified Cox. Okay, now, there's one other thing I did that I didn't do in class because I didn't have time. There's a second example in chapter. What chapter is it? The stratified Cox chapter, chapter 5. Okay, and this is the second example, and it's more complicated. And I want to go over it a little bit, but not too much, because my goal today is to talk about the extended Cox model. So I don't want to spend the rest of the class talking about this example. I want to spend no more than 10 minutes talking about it. Okay. However, in the lab tomorrow, your TAs are going to talk about this. Now, the extent that they're going to talk about it might depend upon whether you have looked at it and read what is in the chapter and looked at these notes to figure that out. If you don't have any questions, they might just pass it by. So it's up to you. But in this example, it's a different data set. It's called the Veterans Data Set. It's a lung cancer trial. It's a clinical trial. There were 137 patients. They all had lung cancer. They're being treated for their lung cancer to see how long they survive. Okay, time until death is the time variable. Okay, and the censoring variable is whether they died or whether they were censored. Okay, and there were a whole bunch of predictive variables that were being considered. And the main one of interest was whether they got a standard treatment or a test treatment that they thought might help prolong survival. Okay, so the question is there a treatment effect? Okay, that's the main question. So you imagine whatever model you're looking at, the hazard ratio, which is survival analysis, will be a hazard ratio. The formula will be some e to the beta type of formula. Beta will be involve the coefficient of the treatment variable, and it may involve some of the other variables depending on whether there's interaction or not in the model. Okay. Well, the other variables that are being controlled for is there's a list here, and one of those variables is cell type, the type of cancer that they have, where the cancer is located, or where or what type of cancer it is. And there's 4 types: large, adeno, small, squamous or squamous. Not sure how to pronounce that. Okay, so there's 4 categories. Okay, so if you were going to put this variable in the model as a predictive variable, and there's 4 categories, what would you do? 3 dummy variables, right? For the 4, you define them whichever way you want. I think I did say on this thing that the squamous variable, the squamous category is going to be the referent category in terms of what I show. And then there's other variables. Another one is performance status, which has to do with how they carry on daily activities. And they get a score from 1 to 100, depending on how easy they are to perform daily activities in terms of walking, dealing with diet, dealing with eating, digesting food, and stuff like that. The disease duration is another variable. Their age in years is another one, and whether they've had prior therapy or not. Yes or no, none or some. These are all predictive variables. So here's a model that involves a whole bunch of variables. Now, here's a slide. Okay, this is the output for a no interaction Cox proportional hazards model with all the predictors in the model. Now, what do we want to do here, given what I've just described and what this output, what's the first thing we want to do? Well, I mean, the main thing we want to do is evaluate whether there's a treatment effect. And if we're doing survival analysis, the first model we want to consider is the Cox model, the Cox proportional hazards model. And we'd like to know whether we could use that model or not. Now, what do we have to do to decide whether we can use that model? Well, we could define what we think the model should look like, and then we could evaluate whether the variables we're putting in the model are okay, that they satisfy the proportional hazard assumption. So this particular table over here gives you some information to allow you to evaluate that. Actually, it allows you to evaluate that for one of the 3 ways to evaluate the proportional hazard assumption, even though there are 3. Remember, there's the log-log curves, whether they're parallel. There's using a time-dependent variable, which we haven't really gotten into, which we're going to start to get into. And then there's what's the other one? The goodness of fit. Goodness of fit that involves using something called Schoenfeld residuals. And I briefly showed you what the output looked like. But although in the lab last time, which you may not have paid that much of attention to because you weren't worried about the code of how to do it, they're going to show you again tomorrow. But anyhow, this is the goodness of fit p-values for the goodness of fit test for when all these variables are put in the model, which is sort of questionable because whether you put all variables in the model together when you're not even sure if some of them should be in the model in the first place is questionable. But this is one way you could check it in any case. So putting them all in here, what do you notice? Well, you notice that some of these are in red. Why are they in red? Because they're sort of significant. I mean, the one over here is highly significant. This is not significant at the 5% level, but it's significant at the 10% level. Significant meaning what? If you're doing the goodness of fit test. Looks like that these variables using this goodness of fit test don't satisfy the proportional hazard assumption. Okay? Now, again, you don't necessarily want to do one test and doing it one way to make this decision. And you're going to get plenty of opportunities on the take-home final to do it a number of different ways. But all I'm trying to say here is that if you were looking at this and trying to make a quick decision about what's going on, you'd probably say, I have to worry about the cell type variable, whether it satisfies the assumption, and I have to worry about this variable, the performance status variable. And if I decide that they don't satisfy the assumption, and at this point the only way I know how to deal with a situation when a variable doesn't satisfy the proportional hazard assumption is to stratify it. I'm going to have to stratify on these variables. So I'm going to have to use a stratified Cox procedure. Now, there is a way to do the extended Cox model. We haven't got to that. We will in a moment. But let's talk about what we're going to stratify on these variables, okay? So there's two variables, cell type, 4 categories, and this variable performance status, which is actually a variable that ranges from 1 to 100. It's almost like a continuous variable. I mean, it could be a number 1.3. So it could be something like that, but it's even if it's whole numbers, between integer numbers, it's still a variable that's almost like a continuous variable. Now, if you wanted to stratify on cell type and performance status, and you wanted to consider 100 different values for the performance status variables, how many strata would you have? How many strata would you have? 100 for the performance variable, and how many for cell type? 4, so you'd have 400 strata, okay? That's painful. You wouldn't want to do that, okay? So what we did here, what I'm describing here is, I took the performance status variable and tried to make a simple thing to say, well, let's categorize the variable. Let's not use all 100 scores. Let's categorize it into a number of groups, but the simplest way is high or low. So I'm taking the performance status variable and I'm dividing it into 2 categories, either high or low. Okay, so there's 2 categories of a new variable dividing from this, and there's 4 categories of this. So how many categories, how many strata do we have if we want to use a stratified Cox model? How many strata do we have? 4 of the cell type, 2 of this performance status variable, which we're now making into a binary. So we have 8 strata. Okay, now when we have 8 strata, what that means is, if we wanted to do the analysis and we wanted to even consider an interaction model, we'd have to run 8 different models if we wanted to do it separately for each of the strata. Whereas if we wanted to run a model where we wanted to consider we wanted to do it using that that model where you can put all the strata together into one model, you could actually do it another way where you didn't have to run 8 models, not 8 different models. You can run one model. Now, in this chapter and in this section, even in the notes, I talk about how you would do that. But I'm not going to go into it in all its glory here. I don't know whether it's glory or not, because it's going to take too much time. But let's talk about this a little bit. Now, first of all, on this slide and the next slide and the slide after that, I go through how you would do the goodness of fit test, what the code would look like. And that's something that was already done quickly last lab, and it's going to be shown, going to be talked about tomorrow, so I'm going to skip that. I want to go to this slide, okay? This slide says, here we're dealing with the following situation. We got these 4 variables, these 4 categories of the cell type variable, and we got a variable performance status that we're going to decide don't satisfy the assumption. So you see where I say cell type, performance status don't satisfy the assumption because these are the goodness of fit values. I would want to use the log-log curves and also using a time-dependent variable way to check this, but I'm just sort of shortcutting that and just saying suppose we've used that and they all confirm this thing. So what we've decided, therefore, that these 2 variables don't satisfy the assumption, and the rest of these variables, as far as we're concerned, given the goodness of fit test, look like they're okay because their p-values were all non-significant. So that would mean maybe what we would do is then stratify on these 2 variables and put these other variables in the model. Okay. So what did we do? Well, what we did was, now I did a shortcut. I did a shortcut here to try to make things a little easier to read. So one thing was the variables listed in the model statement were treatment and age because it looked like treatment is okay and age is okay because they're very highly non-significant. I mean, the 2 goodness of fit. But these 2 variables, what's it called? Duration, disease duration, and prior treatment. I think that's what we're saying. Prior treatment. It turns out if you go back into this, you notice that the chi-square value for disease duration is 0.9920, and the chi-square value for prior treatment is 0.7554. So both these variables are very non-significant if you just look at them by themselves. Okay, now this is again a shortcut, but what I'm saying is I'm going to drop those variables from the model because it doesn't look like they're doing very much. Okay, so what I'm going to do is I'm going to run a model, that has treatment and age in the model because they look like they're okay, and I'm going to stratify on these other two variables, cell type and this binary way of looking at performance status, and by doing that I'm going to have 8 strata. So if you look at this model, and then I'm going to omit from the analysis disease duration and prior treatment because they were highly non-significant. So that's the decision I made at this point. Even though if it was really my data and I really wanted to I would do a lot more than this. I'm just trying to shortcut what you do. But look at this model. First of all, is it a stratified Cox model or a Cox proportional hazard model? We know it's a stratified Cox model. Is it a no interaction model or an interaction model? You know it's no interaction. Why? Because the coefficient beta 1, beta 2 don't have a G there. Okay. So if we fit this model using on the VETS data, what would be the effect, what would be our estimate of the hazard ratio for the effective treatment? For this model, the e to the beta 1, right? It's a no interaction model, and the treatment variable is called Tx, the e to the beta 1. Have I pulled any tricks here? No. I think I have. So, okay. So now, how would you do that? Well, look at the code down here. There's 2 codes on this. The first one is just taking performance status and making it a binary variable. Look at the second code. Look at the second code down on the screen here. See where it says model serve T star status 0 TX age / RL. What am I doing? What's that statement doing? It's putting treatment and age in the model. Just like this model statement saying did. Just like this model saying has treatment and age in the model. What is this doing? The strata statement. What's that doing? It's stratifying on cell type and performance status, right? Now, it's doing it one of 2 ways. Now, it turns out, I said method 1, the short version. It turns out one way to stratify on 2 variables, one of which has 4 categories and one of which has 2 categories, is to put in the strata statement the 3 dummy variables for those 4 categories on 1 variable, and 1 dummy variable for the variable that only has 2 categories, and say strata, and that'll do it. That'll actually define 8 strata without actually having to do it in a very long way. This is the short version. So if you run this, you're going to be fitting this model. Now look at the next slide. See where it says method 2, the long version? Okay. Now what did I do here? I just want to show you, what did I do here? What I did here was I actually defined, you see it says Z1, Z equal to 1, Z equal to 2. What I did was I defined 8 variables, or 8 categories. Why did I define 8 categories? Because there's 4 cell types and 2 performance status. So there's 8 categories. So I'm actually defining the 8 categories. What about the first category? What does this say? Who's in the first category? Cell type 1 is 0, cell type 2 equals 0, cell type 3 equals 0. What are we talking about? That's the reference group, right? And what is this? This is the reference group for the performance status variable, which was 0 meant was low, was worst. Or I don't remember whether it was low or high, but it was 0 is low. So this is one of the groups for the 2 reference groups. This is the group that involves all the reference values. And these are other values. This is not the reference group for cell type because CT1 is 1, so it's not the reference group. So this is another way to do it. Now notice what I did here in the code. The model statement is exactly the same as it was here. TX age treatment. What about the code here? What about the strata statement? Why is it strata Z? Because I've defined a variable z that has 8 categories. So if I write straight a z, I'm telling the computer to do a stratified Cox on a variable that I've made into 8 categories using the 2 variables that I'm stratifying on. So this is one way to do it, and this is another way to do it. So there's 2 ways to do it, and either one of them are fine. Either one is fine. You could do either one. Okay. So if you do that, this is what you get. This is the code. This is the output for what you get when you run this model. Okay, what do you get? Now you notice that you get all this stuff, but look at down at the bottom, TX and age. Why did I put TX in bold? Because that's your exposure variable. Okay. Now, why did I circle this? What is 1.134? What is that? The hazard ratio for the effective treatment controlling for what? Controlling for age, that's all. And it's also controlling for the 2 variables we've stratified on. They're not listed in the model because they're not in the model, but they're controlled for. So this is the hazard ratio I get for the no interaction model. Okay? And is it significant? Not significant, and there's a confidence interval. So it looks like if the no interaction model was appropriate, there's no effect. Just did the analysis. Okay? That's how you do it. Okay? Now, the next issue that I'm going to be taking more time than I want to is, well, what if you wanted to check to see if the no interaction model is not appropriate, you want to do an interaction model. How would you do that? Well, what would you have to do? You notice how it's got beta 1 without a G and a beta 2 without a G? You'd have to put a G subscript here. And that would mean that as G goes from 1 to 8, you're going to have to fit 8 separate models, by separating the data into the 8 strata, and fitting separate models, and then combining that information to get the hazard ratio for the effective treatment on each one of these 8 strata. Or you could use a single model. And the single model, now you notice on this slide, this is as far as I'm going to go with this thing. But on this slide, look at the no interaction model, and then there's 2 versions of the interaction model. Look at this version of the interaction model. What have I done? What does this one in the middle say? One in the middle says is that, like, I'm running 8 different models because I'm stratifying the data into 8 strata according to the combination of cell type and performance status variables that I get. The 4 cell types times the 2 performance status categories. Okay, that's one way to do it. Now, what about this model, the one down at the bottom? Well, this model is equivalent to this model, but it's involving that more complicated formula. This one I showed you very briefly last time, the formula where you can just use one model. And this is where you're going to have to read more about it. But this is, now notice, it's got treatment and age. Now look at the next set of variables in this model. How many variables are in this column, this row? How many variables? And how many variables are there? 7. Right? Can you see 7? One of them is Z1 star times treatment. And the last one is Z7 star times treatment. What are these variables? There's an interaction of a Z variable, the Z variable, with the treatment variable. Why are there 7 variables in here and not 8? Because there's 8 strata, so you put in 7 dummy variables for 8 strata. Okay. Now you notice over here, what about here? What's this? This is also 7 product terms. But this now involves the interaction of the variables you're stratifying on, cell type and performance status, with the other variable that's in the model, age. So this is the model that would be equivalent to this model. Okay, so there's 2 different ways you can do the interaction model, and each way is fine as long as you know how to do it. Okay, and that's what you're going to have to sort of spend a little time learning, and that's what you're going to wind up playing around with a little bit on the take-home final. We're going to have to be able to do this or say something about this. Now, let me ask you this. What if you wanted to test, whether there's any interaction at all? You wanted to do a chunk test for interaction. How would you do that test? How would you do that test? You compare two models, likelihood ratio test. What are the two models? Well, it's either this model with a no interaction model or this model with a no interaction model, because both of these are two ways of saying the same thing. If you were going to use this model to do it, what's the degrees of freedom for the no interaction? No interaction of any kind between the variable you're stratifying on and the variables that are in the model. What's the degrees of freedom? Well, how many parameters we have to set equal to 0? Can you see this is a little complicated? That's why I've avoided this to a point, but how many parameters do you set equal to 0? You have to set every coefficient of every product term in this model equal to 0. How many coefficients are there? There are 7 for the treatment variable. There's 7 product terms involving treatment, and there's 7 product terms involving age with a variable you stratify. So what's the degrees of freedom of the chunk test for interaction? 14. Because you'd have to set 14 betas equal to 0 to do this chunk test. And how would you do it? You'd fit this model, you could do this model and get the log likelihood statistics for each model, subtract one from the other. It's a chi-square with how many degrees of freedom? 14. That's how you do it. Okay, so in this chapter on stratified Cox, and in this set slides, I've got a whole bunch of this worked out with the output and stuff like that, but I don't have time to do that. So you're going to have to figure this thing out, and it's not that easy to figure it out. In fact, this says how would you figure out once you fit the model what the hazard ratios are? Okay, so I'm going to stop with that and start doing what the extended Cox model is, because I got to go on. Otherwise, I'll never get, and I might still not get where I want to be as a result of going on. Okay, so let's talk about the extended Cox model. That's what we're going to do now. This is it. Cox model for time-dependent variables. Okay, that's what we're doing now. Okay, there we go. Okay, this is a list of the things I'm going to talk about. And the first thing on the list is the definition and examples of what we mean by a time-dependent variable. And then the second thing is what the model looks like. So that's the first two things we're going to get to. What are we talking about for time-dependent variables? I've already talked about it a little bit. I want to say a little bit more about it, a little bit more detail about it. Then I want to talk about what the extended Cox model looks like and what you can do with it and all of that. Okay, so let's first look at this slide. Okay, this slide is not that complicated, but let's talk about it. Okay, what's a time-dependent variable? Time-dependent variable. It's any variable that you're going to put in a model, whether it's any kind of model, but some models don't let you put them in there. But if you're talking about a survival model and a Cox extended Cox model, you can put in time-dependent variables, and it's any variable whose values may differ over time. That's what you mean by a time-dependent variable. Now, for example, here's one, gender times time, times t. T stands for time. Is that a time-dependent variable? Well, gender isn't, as long as you're not doing a study where people are changing. Okay, which some people do those studies, but in this case, we're not doing that. So we're talking about somebody their gender stays the same throughout the whole part of the study. But this part of it is time independent, but when you multiply it by time, and time is moving on, this is a variable whose values are changing over time. When time is equal to 1, it's gender times 1. When time is equal to 2, it's gender times 2. If we're talking about days, weeks, months, or whatever it is. So this is a time-dependent variable. Okay. What about this one? E stands for exposure status. And then there's times look at this, log t minus 3, okay? Is this variable a time-dependent variable? And the answer is, even though the E variable might be time-independent, you're either exposed or unexposed, say, it turns out that when you multiply it by some term that's a function of time, then you've got a time-dependent variable. In other words, the values of this variable is going to change depending on how time changes. When time is equal to 1 or 2 or 3, this is going to change from log of 1, which is 0 minus 3, to log of 2 minus 3, and so this variable is going to change over time. So these are two examples of time-dependent variables. The second one's a little bit weirder because it's not simply time, it's some weird function of time, which is allowed. Now, in fact, one reason why people often put in a minus something like this is that there's something called the lag function. Sometimes when you're dealing with survival, it may turn out, if you think about it, it may turn out what your the value of a certain variable at a certain time, it may take a while before that variable has an effect. It may take a lag. It may take 3 weeks. So if you want to do something to reflect that, you can subtract 3 or something like that to say it's not just the time, it was 3 weeks before what that variable was when it has an effect. Anyhow, that's why sometimes you can put this in. But anyhow, the point about this is these are two examples of time-dependent variables. Now, here's 3 other examples. E of t, SM, K of t, and WGT, weight of t. Now, these variables are different from the first list. And the reason, these are called internal time-dependent variables, and this is called a defined time-dependent variable. The reason why these are called defined time-dependent variable is because once you know the time-independent part of that variable, this is the time-independent part of this variable, this is the time-independent part of that variable. Once you know whether somebody is male or female, you know all the values of that variable. Okay? But now, if it's an internal time-dependent variable, you never know what the values are. You can't specify what all the values are. They change from one time to the next. So it's internal to what the person's status, whether the person's exposed or not, depends upon whether they're in a industry, they're getting exposed to a chemical, whether they're exposed this day or that day, or how much exposure they have, that's changing, and you don't know what it is. And if this is the kind of variable you want to put in the model, their exposure at time t, their smoking status at time t, if you're doing a study where you're trying to get people to quit smoking, or their weight at time t, if you're trying to get people to lose weight. And then there's a third kind of variable that, in a way, it's not that important to make the distinction between the last two, internal and ancillary, but air pollution index at time t. In other words, you might be worried about whether what somebody's exposed to outside, whether to what extent that affects whether they can breathe well, their FEV, their lung capacity, something like that. Okay. And so you may have a variable like that, and that it turns out that when you try to measure that variable for any individual, well, what happens one day changes from the next day. You have a lot of pollution one day, you have less pollution the next day, so that variable changes over time. Well, you could say this kind of variable is not exactly internal because it's external. It's going on whatever's happening, whichever individual you're talking about. It's ancillary to the individual. That's why it's sometimes referred to as an ancillary variable. Although it's still sort of internal because until you see what happens with that individual, you won't know what the value is. But anyhow, what I'm trying to say is the first list of variables differs from the other two rows because first one, you know what's going on once you specify the time-independent variable, part of it. But for these other variables, you can't specify what the values are until you see what's going on with every individual over the time that you're doing the study. You look at the individual's exposure status over the whole time that you're following them. Okay? So now here's two other examples. Heart transplant status at time t. Okay? Now, as you know, people get transplants nowadays. Now, there was a time where that was a key question. Early on, whether that transplant, whether getting a transplant even worked, whether that saved you, whether that actually would help save you and save your life. So when in the original studies to deal with whether transplants would work, what would happen is, it still happens now in terms of how you get a transplant, what happens is somebody gets identified to have a need to have a transplant because they have a serious heart condition, okay? And their doctors, whatever, make that decision together with them and their family. And then what happens when a decision is made, you need a transplant? What happens? Do they get the transplant the next day? Why not? Because you have to get a heart to make the transplant. So in order to get the heart to make the transplant, somebody has to come along to donate the heart, and it has to be somebody that somehow their heart and your heart make some sense, some biological sense to be able to put their heart into, to replace your heart with their heart. Okay. So what happens here is, you see, this is the issue, is when somebody gets identified to be eligible for a heart transplant, what they have to do is they have to wait until they get a transplant, right? They have to wait, okay? So what happens is, from the time they're identified, there's time that goes by while they're eligible, okay? It's wait time, okay? And time goes by, and if they actually wind up getting a transplant, okay, then all of a sudden they got a transplant. So if you think about this, what we're talking about is a time-dependent variable. Think about this variable. It's 0 while they're waiting, and then it changes to 1 when they get the transplant. See that? It's 0 while they wait. Now, they may have to wait 2 months, and then it changes to a 1. Somebody else may have to wait 4 months, and then it changes to a 1. Somebody else may have to wait forever, and they never get a transplant, so it's always 0. So that's another time-dependent variable of interest, and that's what was still used when people trying to look at heart transplant status, and it's a time-dependent variable problem in terms of you have to wait to get a transplant, okay? Now, there's another kind of variable here that's a time-dependent variable that is often used when you're dealing with variables that don't satisfy the proportional hazard assumption. And this is a variable E times G of t, where G of t is a very specific function of time. G of t takes on the value 0 if t is less than or equal to some value of time, and equal to 1 if t is greater than. So let's say, we had an example. Let's say t sub 0 is 3, and we're talking about 3 days. Remember I gave you an example about people getting surgery for cancer? Okay, suppose we decide to define a variable G of t is 0 if t is less than or equal to 3 days, and it's equal to 1 if t is greater than 3 days. Okay, what does this variable look like? When t is less than or equal to 3 days, what's the value of this variable? E times 0, so it's 0. Right? When t is greater than 3 days, what's the value of the variable? E. Okay. So the variable changes from 0 to E depending upon what happens up to 3 days versus what happens after 3 days. Okay. This is one way one can actually deal with a situation that I described earlier, but we're going to actually look at it for an example. Probably won't start that until Thursday. An example where you think the proportional hazard assumption isn't satisfied, but maybe it's okay before 3 days, and it's okay after 3 days, and you want to be able to put that into a model to allow that to happen, to reflect that. So this is a certain kind of variable that's often defined, and it's called, this function, or this G of t, this kind of function is called the Heaviside function. That's the kind of thing. So there are a lot of survival models that are used that involve something called Heaviside function. Okay? Now, this is sort of a joke, but nobody's going to laugh because I already showed you somebody's drawing of me, But anyhow, Heaviside is not spelled with the I here is not spelled with a Y. because there was a person named Oliver Heaviside. Not very funny, right? But this is the guy. It was an interesting guy. There's a whole little story about him, but this is what he looks like. But he's the guy that suggested using this kind of function to deal with a situation when the proportional hazard assumption isn't satisfied. I'm not even sure if he knew what the proportional hazard assumption was, but he's the guy who had the idea. So it's Heaviside with an I, not with a Y. Okay, forget that. Okay, so now let's go out further. I've now talked about different kinds of variables. Let's look at what the Cox model looks like for the extended Cox model. Here it is. Here's the extended Cox model. Okay. Now, the first thing you notice about this is that it's written in the form of, is it a survival function or hazard function? Survivor function or hazard function? Hazard function, why? Because of the H for hazard, okay? Now, you notice it's written as H of T. You know, previously when I talked about the Cox proportional hazard, it was HT of X, but it was X without a T, because the proportional hazards model, all the X's were considered time independent. But if you're going to allow time dependent variables in the model, then you're going to want to write it not X without the T, you want to allow X with a T in there. So some of the variables in the model are going to be time dependent. So here's the model, okay? It's a hazard function. There's a baseline hazard, just like there is in a Cox proportional hazards model, but this is an extended Cox model. And then the right side of the model, the exponential side, has two different kinds of variables. The first set of variables, beta ixi, first set of variables, there are p sub 1 of them, there might be 3 of them, p sub 1 might be 3. These are variables that, as far as you're concerned, are time independent. That could be a treatment status variable, either you get the treatment or you don't, it doesn't change. Okay? And then there are some other variables in the model that are time dependent. So an extended Cox model allows you to have both time independent variables and time dependent variables in the model. That's what an extended Cox model is. It's, you know, if I didn't have this last part, the second sum, what would the model be? It would be a Cox proportional hazards model, right? If I didn't have the right sum over here with xj of t, I would be having all the variables in the model would be time independent, and I'd be talking about a Cox proportional hazards model. By adding these variables in the model, I'm making it a different model. I'm putting in some time-dependent variables. So that's why it's called the extended Cox model. Now, one of the things important to say about this is, okay, these are time-independent variables. These are time-dependent variables. Notice one other thing, that first of all, there's this time-dependent variable x sub j. It's the jth time-dependent variable of the time-dependent variables in the model. Okay, but you notice there's a coefficient, delta sub j. Delta sub j is the coefficient of x sub j of t. What you don't see, the way this is written, you don't see delta sub j times t. You don't see delta sub jt. You don't see t involved in the way delta is defined. It only involves j. So what you're saying is the effect of this variable has some kind of global effect. It doesn't depend upon t itself. T is changing, but when you want to talk about e to the beta or e to the delta in this case, it's not e to the delta involving t. I mean, t is involved in the x, but not involved in the delta. So that makes something very kind of a little bit weird, a little bit unusual about this model. So that's what the extended Cox model looks like. Okay. Now let's look a little further into this thing. Well, first thing is, how do you fit this model? How do you fit this model? What the answer is, and all I say on this slide is, you use a program that does maximum likelihood estimation. That's how you fit it. And the program, if you're using SAS, is PHREG. So that's the program that will fit a Cox proportional hazards model and an extended Cox model. That's the program you use. Okay. And the way you do that is, you know, it's just maximizing a likelihood function. Turns out the likelihood function and the process is more complicated when you have time-dependent variables than when you have time-independent variables only. When you have time-independent time-dependent variables, remember I talked about the risk set and how the risk set changes as people fail? Well, it turns out not only does the risk set change, but the value of the variables, the predictive variables change if you got time-dependent. And that makes everything a little more mathematically complicated, but who cares? You got a program that'll do it, so you're not going to worry about that. If you're trying to do some mathematics with this, then you're going to worry about it, but none of you are doing that, I think. So it's maximum likelihood estimation. You fit the model, you do likelihood ratio tests, you do wall tests, you get e to the betas, you get hazard ratio, same thing. Okay, so now let's look at the characteristics of the extended Cox model. Let's now look at the characteristics of what does it mean? What does it say? Okay, well, here's what I've just written the model again. Now look what I say underneath it. I say this model assumes that the hazard at time t depends on the value of x is time independent, so it doesn't change. But it depends on the value of the predictive variables at that particular time, not at an earlier time, not at a later value. The value of the hazard depends upon what the value of x is at that time, not a different time, at that time. Now, if you're worried about that, if you're worried about what the value is, we talk about people who are, one of the classic examples is, I've talked about this, recidivism. You know, when you talk about people who go out on parole, okay, and they go out on parole, and one of the first things they want to do is try to get a job, try to get employed. So you might have a variable called employment status that you're measuring. Well, it may turn out that when somebody goes out on parole and they try to get a job, it may turn out that they don't get a job right away. It takes a while because they did something wrong. You know, they got arrested, something like that, and they're on parole. Well, it may turn out that after a while of not getting a job, they have an effect of doing something to get rearrested. There may be a lag from the time that they first measure their employment status until the time they actually do something to create something to get rearrested again, so they lose their parole status, recidivism, something like that. If that's the case, you may want to do something. You may want to say, well, I don't care about what the value is of this variable at time t. I want to compare about what the value of this variable is 3 days or 3 weeks before it was first measured, because that's when it started to have an effect. It doesn't happen right now, it happens earlier. That's when it starts to take an effect. So that's why people might want to do a survival now where they actually consider a variable where they change the original variable to something that reflects some kind of a lag. Okay, that's a little complicated, so I'm not going to get into that in any big way. I'm just saying that you could do that. Okay, but this is the model. This is the model, and it does assume that if you're not putting a lag in, you're saying the value of the variable at time t is affecting the hazard at that time. It's affecting their potential for failing at that time, not an earlier time, okay, or a later time. Okay, now let's talk about the hazard ratio formula. Hazard ratio formula, okay. How do you get a hazard ratio for this model? What do? You say, let's get the hazard for one person, and let's divide it by the hazard for another person. That's what we did when it was a Cox proportional hazards model. Okay? So if we do that, we talk about two people, person X star and person X. And let's say we talk about what the value of person X star is at time t, and we compare that hazard for a different person at the same time t. So we're getting the hazard ratio for two different people at time t, at a given time. Okay? If we do that, what happens is when we take this thing for the X star, we divide it by this thing for X, and the baseline hazard, like it did for the Cox proportional hazard, drops out. H naught of t cancels out. So when you take the hazard for one person divided by another, this is what you get. Now look at this expression, first of all. If you didn't have any time-dependent variables, you didn't have this right side, you just had this part of the expression, what does that look like? That's the old formula for the hazard ratio for Cox proportional hazard model. It's the e to the beta times the difference between corresponding x's for the time independent variables. okay? That's what it is if there were no time-dependent variables. But if there are time-dependent variables, then the formula is a little more complicated because it involves this part, this component, and involves this component, okay? Now, this component involves the difference between two people's values of two different variables, of the same variable, two different values for two different people at time t. And this says this is dependent upon time. Since the values of these variables depend upon time, this means that this part of the formula depends upon time. So in theory, in terms of what this expression says, it means the hazard ratio depends upon time. Meaning that the proportional hazard assumption isn't satisfied. Remember, what was the proportional hazard assumption? So you take the hazard of one thing divided by the hazard for the other thing, doesn't matter, it's independent of time. That's what this part says, but that's not what this part says. So what I'm trying to tell you here is that if you have an extended Cox model, theoretically, you set things up so that the proportional hazard assumption isn't satisfied. That's what you're doing with an extended Cox model. If the proportional hazard assumption is satisfied, then you use the Cox proportional hazards model. Okay, so now, that's what this says, okay? Now, so I say the hazard formula theoretically depends on time. However, in practice, there may be some situations when you can say the hazard ratio is independent of time, and I'm going to give you some examples of that. That's what I'm going to do before we quit today. Okay, I'm going to do before we quit. Now, there are two situations. Okay, that's the formula. There are two situations. One is when you're dealing with a defined time-dependent variable, and the other one you're dealing with internal or ancillary. Let's look at this thing. Look at this model here. It says example. See example? Look at this model. This model right here. Can you look at this thing without having a nervous breakdown now? I know it's 5:15, so you're starting to get nervous because you want to get the hell out of here, maybe. I don't know. But look, it says E is a 0-1 time-independent exposure variable. Look at this model. There are two variables in this model. One is E, and one is E times T. So there's two coefficients in this model, okay? Now, suppose I fit this model, well, I use this model, and I say, what's the hazard ratio comparing somebody who's exposed? And again, exposure is time independent, so they're always exposed, or they're always unexposed. What's the hazard ratio comparing exposed people to unexposed people? What is it? Well, I write the hazard ratio for exposed people, and you notice E is now 1 over here, and E is 1 over here, right? I'm plugging in 1 for E in the numerator, and I'm plugging in 0 for E in the denominator. And when I do the algebra, the baseline survival curve, the baseline hazard function cancels out. And what happens here? Well, this is E to the, what is this? E to the 0 plus 0. It's E to the 0, which is what? 1. So what happens, what do we wind up with? We wind up, these cancel, and it's E to the what? Beta 1 plus delta 1 times T. See that? That's the formula for the hazard ratio. So what does this say about the hazard ratio? It says the hazard ratio is going to depend on time because the formula for it has time in there. So if you go from time equal to 1 to 2 to 3, what happens to the hazard ratio? If delta 1 is positive, let's say delta 1 is 2.1, positive number, okay? It doesn't matter what beta 1 is, but let's say beta 1 is positive and delta 1 is positive. And T is increasing because it's going from 1, 2, 3, etc. Start with 0, goes 1, 2, 3. What happens to the hazard ratio if delta 1 is positive? It's increasing, right? That's what this model says. So that's an example of a situation where if you have a model and you're using an extended Cox model, then you're saying the proportional hazard assumption isn't satisfied. The hazard ratio isn't constant over time, it's changing over time. Okay? Now let's look at the second example, which is a little bit more confusing here. Suppose we're dealing with an exposure variable that's an internal variable. People change their exposure status. A given person can be exposed one day and not exposed the next day and exposed the day afterwards and change around. Okay. So now suppose we want to compare two people. We want to get the hazard rate. So this is our model. We got this variable, E of t, which is changing for any one person. And suppose we now talk about two different people. One person who's exposed at time t, and another person, a different person, who's unexposed at time t. We want to say, okay, what's the hazard ratio comparing the person who's exposed at time t with the person who's unexposed at time t? What's the hazard ratio? Well, if I plug in the value for E of t, it's 1 here in the numerator, and it's 0 in the denominator, so I get e to the delta. What do you notice about that? Does that depend upon time? It's independent of time. Okay? So in this particular situation, you can have a internal time-dependent variable where the hazard ratio is independent of time. Does that mean the model is now a proportional hazards model? Doesn't mean that. It means you're still doing an extended Cox model, but you could have an extended Cox model where the hazard ratio doesn't depend upon time. That's what this says. But what does this mean? That's another issue. What does this mean? You notice that E of t is not a variable that's always one value. For a given person, it changes. Okay? So if we're talking about the effect of exposure on the survival or on their hazard or their potential for failing, we're not talking about the effect of exposure at any particular, we're talking about something over all the times we look at a given person and we compare it to another person. What's the effect of exposure? So you see, e to the delta represents an overall effect of this time-dependent variable. It doesn't represent an individual effect at one particular time. It represents some collective effect of what's going on when we consider the fact that individuals are changing over time. So even though you could say the hazard ratio is constant over time, it really means something different than it would mean is if E of t was being replaced by a time-independent variable. It means something different. So, in fact, let's look at one other example here. Well, another way to say this is that the hazard ratio compares an exposed individual to an unexposed individual at the same time t, where the hazard rate for exposed is based on person time accumulated while exposed, and the hazard rate for unexposed is based on the person time accumulated while unexposed. What does this say? This say down at the bottom. It's a little tricky. What does it say? Well, you've got a variable, E of t, and a given individual can change their exposure status. So if you talk about a particular individual, their exposure status changes from 1 to 0 all throughout the whole time. What you say is, while that person is exposed, they're going to contribute information to failing for people who are exposed. While that person's unexposed, this person is going to contribute information for people who are unexposed. And that's what this statement means. It means the hazard rate for exposed is based on the person time accumulated while exposed. If you have 3 individuals, and individual 1 is exposed at some times and not exposed at other times, and individual 2 is exposed at some time and not exposed, what you're doing is you're sort of accumulating the exposure information for all those individuals. That goes in the numerator. And what you're doing for the people who are unexposed, while they're unexposed, you're putting that in the denominator. Now, I realize what I'm saying is not easy to understand. This is confusing. This is not a clear-cut thing. So you might have to think about it, and you might want to talk about it during the lab. Okay? So that's sort of, now, let me just show you one other example here. Look at this example. Look at this example. How does this example differ from previous example? There's the example on, what was it, slide 12. And now I'm going to slide 14. What I've now done is I've added another term. So I have a variable that's an internal time-dependent variable, E of t, and then I've put in addition to that a variable t times E of t. What about this variable? What about this model? What's the hazard ratio for this model? Well, the hazard ratio for this model is when you compare somebody who's a 1 with a 0, you're going to put in a 1 over here and a 1 over here, and you're going to put in a 0 over here and a 0 over here, and this is what you get for the hazard ratio. So what does the hazard ratio say here? In this case, the hazard ratio is dependent on time, because not only are you dealing with an internal time-dependent variable, you're dealing with a variable that's a product of an internal time-dependent variable with time, sort of an interaction with time of that variable. So it turns out that you can have an internal variable in one case where the proportional hazard assumption seems like it's satisfied, depending on the model, and maybe not satisfied, depending upon the model. Okay. Again, this is a little difficult to understand. That's why we wait to talk about this until at this point near the end of the course. Now, that's sort of the last thing I'm going to do today. What I'm going to do at the beginning of the class on Thursday is I want to tell you how you actually use the computer to get estimates of these variables. What you do with the computer. That's the thing I'm going to start with on Thursday. And then we're going to look at some examples and try to figure out what those examples mean. So up to this point, there's a little theory here, conceptualization, that's not that easy. And I got to admit that. It's not that easy for me to even talk about. Okay? Just doing the best I can. Okay, see you on Thursday. Go Heels. Megan. Okay. Oh, did I already erase something that I shouldn't have?
No, I was going to see if you wanted to stop it.
Yeah. I don't want to get you on the, I don't want to get your stupid question on the, no, that's okay. Doesn't matter. That's okay. Your smart question.
I'm just going to let you know that I'm going to Chapel Hill this weekend.
For a job interview or
No, my boyfriend played basketball at Chapel Hill.
You're kidding?
Yeah.
In the high school or UNC?
At UNC. He walked on his senior year.
He did?
Yeah, so we're
I met him.
Yeah, you did.
Mm-hmm. What's his name?
James Gallagher.
James
Gallagher?
Gallagher, oh yeah.
And his grandpa,
he's a walk-on.
His grandpa taught at UNC forever.
Wow.
School of education. So we're going up there this weekend.
And they,
football game and basketball.
Well, they have their first game against. Is it home game against Temple?
Yeah.
Oh.
So we're going to the basketball and the football game.
Well, it's interesting because the football is pretty good, and basketball, their key player got hurt.
Yeah.
You know about Marcus Page?
Yeah.
Broke his, so he's not playing. Now they got a really good team, but he's the
Hopefully his wrist is healed by the time we play really good teams.
Yeah, but Temple's usually pretty good.
Yeah.
So
it'll be a good game. But I saw your shirt when you walked in.
That's right.
Okay.
That's right. Okay. And I knew I had something to give you. I knew I had something to give you.
Thank you.
Okay. Check it out. Okay. Check it out. Eugene.
Yeah.
Right?
I had to come up to say hi to Victoria.
Oh, you're talking.
I am, yeah. I went to undergrad.
Well, Megan, she's going to this week. She's going to see basketball.
Okay. Yeah, homecoming was this past weekend, but I wasn't able to go. Yeah.
166.
Crazy. Yeah.
So you just you missed it when they won. When they won the championship. Because they won with
But I was there when and those were, I was able to get tickets for both of them.
I gave up my Tar Heel tickets to the Hawks. So I also gave up to see the Braves, but I gave up the Braves. Yes, you're going to go up there and practice Tar Heel, but you can all the games. All the basketball games are televised.
Yeah, there's also like an alumni network that watches the games.
They often go to this place called Jocks and Jill. Trouble is, you see, I can't handle it. When they're playing, I have real hard to.
Stress, yeah. Especially during the two games.
And then last year, right out here, nice and little car. So where are you from?
North Carolina still. Yeah, my family's from North Carolina.
These are you guys. And the star player is the guy in New York. Player of the year. I'm listening to this. Any questions about anything? Yeah.